This law played a pivotal role in unveiling the mysteries of our cosmos. There is no gravitational field around him, and all the laws of physics work as expected. Have you ever wondered why a stone thrown upward always returns to the ground? Or why your phone slips from your hand and inevitably meets the earth? If everything is so eager to fall to the ground, then why doesn't the moon also come to earth? Why is the earth for endless ages circling around the sun? These phenomena are all governed by a fascinating force that shapes our universe, gravity. I'm sure many of you have heard about gravity at some point, but how many among you truly understand it? Even a four-legged animal knows at least this much. He needs to descend carefully from a height, or else he would fall. But gravity is not just that. It holds much more significance. So how does gravity actually work? To understand this fully, make sure to watch this video until the very end. This story began when our ancestors started observing the motion of planets in the vast expanse of cosmos, among the stars. Eventually, they concluded that all planets revolve around the sun. This realization was later rediscovered by Copernicus. After numerous experiments and observations of planetary motion in space, Kepler unearthed beautiful and simple laws of planetary motion. Firstly, he found that all planets move along a spatial path around the sun, an elliptical path, where the sun resides at one of the ellipse's foci. This was a remarkable observation. Alongside this, Kepler also noticed that the speed of planets' revolution around the sun is not constant. It changes. When a planet is closer to the sun, it moves faster, and as its distance from the sun increases, its speed decreases. However, this change in speed follows a specific pattern. It is not random. There is a mathematical principle that ties the distance between the sun and the planet to the planet's time of revolution. This principle states that a planet's aerial velocity remains a constant of motion. In simple terms, a planet's radius vector covers equal area in equal time, regardless of its speed, whether fast or slow. Kepler eventually discovered a third law of planetary motion after a long time. This law was different from the first two laws, as it related the motion of two different planets to each other. According to Kepler's third law, the square of the time period of the two planets and the cube of their orbit's radius are in proportion to each other. While Kepler was busy studying the changes in our solar system, Galileo also became quite eager to explore the laws of motion. He uncovered a fascinating fact about the motion of objects. An object in motion will continue to move in a straight line unless an external force acts upon it. This principle is known as the law of inertia. Later, Newton made efforts to deeply understand this law and explained that to change the speed or direction of a moving object, a force is necessary. For example, when we tie a stone to a string and swing it in a circle, we need to constantly pull the string towards us to keep the stone moving in that circular path. The heavier the stone, the more force we have to exert. The fascinating aspect here is that we do not need to apply any force in the direction of the stone's motion while swinging it in a circle. As long as someone tries to stop its motion, it will continue moving in a straight line due to inertia. We only need a central force to change the direction of its motion, and that central force is applied to stone through the string by our hands. Similarly, in our solar system, all planets revolve around the sun using the same principle. The sun acts as an invisible force keeping all the planets in orbit. Considering these fundamentals of dynamics and observing the accurate predictions of Kepler's three laws, Newton formulated the law of gravitation. Newton already had an inkling that there is some force that binds us to the earth. Taking all these aspects into the account, he formulated his law of gravitation, stating that any massive object exerts a force on other massive object, an attractive force. The magnitude of this force is directly proportional to the masses of the object and inversely proportional to the square of distance between them. In simpler terms, heavier objects experience a stronger force, and As the distance increases, this force diminishes rapidly. Newton's law explains a range of events, from objects falling to the ground to Earth's orbit around the Sun, and even led to the discovery of new planets in our solar system. This law played a pivotal role in unveiling the mysteries of our cosmos. It provides an easy solution to many cosmic enigmas, such as explaining the shape of our Milky Way. At its center lies a colossal celestial body, a black hole, which compels stars orbiting around it due to its strong gravitational pull. Even the formation of massive clouds and clusters of stars and galaxies in space is a result of the attractive force between masses. However, despite Newton's law of gravitation explaining various local and universal phenomena and yielding desired results from calculations, it wasn't entirely accurate, as realized by Albert Einstein. Einstein felt that if an external mass were placed in a gravitational field, it would instantaneously affect other masses without any delay. This concept seemed unrealistic to him, given that no signal can travel faster than the speed of light. This raised a question: how can Newton's gravitational force act on distant objects without any delay? Einstein's general theory of relativity suggests that gravity is not a force but rather a kind of illusion, a result of the curvature of spacetime. According to Einstein, imagine a man falling freely from a roof. In that state of free fall, he wouldn't feel his own weight. For that duration, he becomes weightless and any object falling alongside him remains stationary. This situation is similar to what a person in a spaceship moving freely in deep space experiences. They would also feel weightless, and objects around them would remain stationary or start moving in a straight line if nudged gently. This man falling from the roof is an example of an inertial observer. He is not accelerating. There is no gravitational field around him, and all the laws of physics work as expected. The remarkable thing here is that the falling man and the person freely moving in space have exactly the same conditions. Neither is under the influence of a gravitational field, nor are they accelerating. However, there is a twist. The falling man is clearly accelerating because his speed increases by 9.8 meters per second every second. Einstein's equivalence principle highlights one key aspect to focus on: the observer's experience. If an observer feels weightless, then they are weightless. In that scenario, no acceleration or gravitational field can act on them. They are in an inertial frame. Now let us consider a spaceship moving at a constant velocity in space and approaching a massive planet. Definitely, the planet will exert its pull on the spaceship, causing its path to bend slightly towards the planet. An observer outside can easily perceive that the spaceship is changing its path and increasing its speed. However, the person inside the spaceship won't feel any acceleration or the planet's gravitational field. From their perspective, they remains an inertial observer. So, how do we explain the curved path without invoking a gravitational field? The answer lies in the curved spacetime. Yes, you heard it right. While the person inside the spaceship continues to move in a straight line, to an observer at a distance they seemed to be following a curved path due to the planet's gravitational influence. This happens because spacetime around the planet is curving. Imagine this: when you travel by aeroplane between 2 points on Earth's curved surface, you follow a path that seems to be straight to you, but due to Earth's curvature, it appears curved to an observer far away. A straight line drawn on a curved surface is called a geodesic. In this analogy, gravity isn't a force, it is an illusion created by the curvature of spacetime around massive objects. Matter informs spacetime how to curve, and spacetime informs matter how to move. Let us imagine you and a friend are standing on the equator of Earth, about 1000 km apart, and both of you start walking together in straight parallel lines towards the North Pole. As you move closer to the North Pole, the distance between you and your friend decreases. You will start coming closer to each other, as if an attractive force is acting between you, but there is no actual force at play. It is due to the curvature of Earth's surface that you are being drawn towards each other. This is exactly what happens in spacetime due to the curvature. Masses attract each other. Einstein's general theory of relativity and Newton's law of gravitation both yield correct results, but general relativity better explains various subtle phenomena. For instance, light also bends around massive objects like the sun, which is not easily understood using Newton's law of gravitation. Alright, we have understood that gravity is not a force. Rather, it behaves like a force due to the curvature of space-time fabric, and it is possible that in future we might develop a successful quantum theory of gravity. But in understanding that, we have not fully grasped the reason behind gravity, the machinery behind gravity. Why matter curves space-time? These questions are logical, but a logical answer based on observation or measurement might not be possible. Some form of imagination will likely to be involved. In fact, when a significant mathematical law is working well, physics does not necessarily get too eager to understand the machinery behind it. Instead, it is interested in comprehending the results and consequences. What do you guys think about it? Let me know in the comments. Please like and share and do not forget to subscribe.